So today we would like to cover a bit of nano fabrication technique. So in nano fabrication, uh, we are going to cover mainly photolithography and e-beam lithography technique. Okay, but let me tell you that there are two approaches in nano fabrication. One is bottom-up approach. Okay, and the other one is top-down approach. What is top-down and what is bottom-up approach? In the bottom-up approach, we basically there are many techniques, usually using chemical technique, or I mean in bottom up technique is usually ideal for self assembly kind of atoms or molecules, okay, into a nanostructure. This technique leads to like molecular scale electronics, where molecules can be designed with specific electronic functions, okay. And bottom up approach includes, I mean, man-made synthesis of for example nanoparticles, nano pillars, nanotubes and so on, okay. um, so this is kind of bottom up approach, where you started with an atom or a molecule and then you will build on that, okay, to your structure. Whereas in case of top down approach, we can create nanostructure out of, say, from microstructures, okay. um, so for example, top down approach is, for example, lithography is a top down approach, okay. um, Whereas here this is kind of a self assemble approach, where you as I said, you start with some atom or molecule and then build on that, so that you end up with your desired nanostructures, okay. Now the thing is, here today we would like to discuss mainly lithography technique, okay. We'll mainly cover uh, photolithography, and e-beam lithography, okay. So these techniques are more controllable. So this top down approach is more controllable, okay. uh, in fact, in our microelectronics fabrication process, we heavily relied on this lithography platform, okay. So as I mentioned, we will mainly discuss photolithography and e-beam lithography. Many of you probably know about photolithography already. uh, in typical photolithography process, what we do, or what we need a we usually need sophisticated clean room, okay. We need clean room. This clean room can be of, what is clean room? Clean room is a room where you implement your lithography processes. And this clean room, there may be different classes of clean room, like class 100, class 1000, okay, or maybe class 10,000. What this number means? So class 100 means there will be less than 100 number of particles of size around 0.5 micrometer or large in per cubic foot. Okay, so similarly class 1000 means maximum 1000 particles are allowed of dimension 0.5 micrometer or large per cubic foot. Okay, so this is how we define clean room, and we do our fabrication processes usually in clean room. These clean rooms are very expensive to maintain because you, as you understand, you need to continuously run air through it with high filtering system. Okay, and the maintain of clean room is very expensive. Now, what are the steps in photolithography process? The steps in the photolithography processes are like you need to start with your substrate or your wafer. Okay, you have to clean it. There are different approach, say your silicon wafer or silicon substrate. Okay, you need to clean it. There are different approaches for cleaning. Particularly we clean the wafer because there may be various kinds of contaminants on the top surface. Okay, there may be oxide layer, native oxide layer, which you need to remove. Okay, native oxide layer might be there. There might be different kinds of ions, sodium ion, potassium ion, different dirt may be there. Okay, so all this needs to be removed from the surface so that you can use the wafer to develop a device. Okay, to fabricate a device. So cleaning is a very important role, very important aspect for fabrication. So after cleaning you do basically lithography. Okay, so what are the typical steps of lithography? So you need to grow a masking film. Okay, so this masking film may be made of SiO2 or may be made of silicon nitride. Okay, so this oxide or silicon nitride layer you need to grow or deposit on top of your silicon wafer. Okay, then you need to coat this with photoresist. Okay, what is photoresist? Photoresist is basically a polymer which is photosensitive. Okay, so you need to this is your silicon wafer, this is your SiO2 or Si3N4 layer. On top of that you coat your photoresist. So you put a drop and you spin coat it, you rotate it. Okay, so that you end up with a thin layer of photoresist. This thin layer should be uniform and the thickness of the layer can be optimized or should be optimized, because if it is too thick there will be consequences, if it is too thin there will be consequences. Okay, so depending on the nature of the resist, whether how viscous it is, okay, or how dense it is, and also the rotation speed, okay, and how long you are rotating, you will get a thin film of photoresist. Okay, and in the lab we optimize this rotation step uh, and nature of photoresist, what photoresist we are using, we put a drop of photoresist and then we rotate the substrate so that it spins, the resist will spin on top of the substrate and form a thin layer. Okay, then what you do, you use, sorry, my pen still is not not properly working. So I am looking at the screen to write what I am writing. So sometime I am writing in the wrong place. Uh, so, so what you now need to do, you need to put a mask. You need to put a mask uh, on top of the substrate. So this is my substrate. Okay, silicon. So in between, what you have to do, uh, you have to bake it. So here you have to bake it. It is pre-baking. Okay, say around 90 degrees centigrade or so. You bake this substrate so that the resist will stick properly on the on this SiO2 surface. Okay. Then what you do, you put a mask on top of the substrate. So this is my SiO2 layer. This is my photoresist. Okay. And on top of that, you put a mask. So this mask is usually made of chrome glass. Okay. Usually made of chrome glass. Okay. So this mask will have some opaque space, some transparent space. So this may be my opaque portion and this portion may be transparent. Okay. So you pass UV light through this mask. Okay. So once you pass UV light through this mask, what you do? So that will change the resist property where it is interacting with the UV light. Okay, that will change the property of the resist here in this portion, because UV light can go through this transparent part of the glass, but it will fail to reach the photoresist on this opaque portion. Okay, so this part of the resist, the property will change. Okay, where it is interacting with the UV light. So then you do post baking. So post baking means you again put it in the oven and heat it up. Okay, and you use some developer. Okay, you use developer to develop the resist. So you end up with you use a developer. Okay, so this is my oxide layer, and when you use developer, the resist here will remain. Okay, sorry about this. The resist so this is my oxide, this is my resist, and you see the middle, from the middle portion, due to this developer will remove this middle portion. Okay, why it will remove the middle portion, that we will discuss little bit later. But we use post baking, that is we keep the wafer again maybe half an hour within the oven, so around 120 degrees centigrade I think. Okay, but again that depends on the nature of the resist and all that, right? Then what you do, you etch, you use etching. Etching means cutting or removing. Okay, etching of the oxide layer. So if you etch, then we will have oxide layer here. Okay, and on top of that there are resist, and you remove oxide layer from here, you see. Okay, maybe using buffer HF. So there are different etchant that can be used to remove oxide. If it is silicon nitride, there are different etchant to remove silicon nitride and so on. Anyway, so you need to remove this masking layer from here, and then you strip off you strip off your oxide, and you end up with, sorry, you strip off your photoresist, so you end up with this structure. So then you have a window where you can make your device, or you do whatever you want. You can epitaxially grow some layer, you can dope this portion, because this portion is now open for further processing. So this is basically photolithography process steps. So let me repeat it once more. So we start with a silicon wafer, say I am talking about silicon wafer only. We clean the wafer. The reason we clean it, because it contains, often it contains native oxide, so you need to remove that native oxide. It might contains different ions, sodium ion, potassium ion, that usually come from our finger or from somewhere. Okay, some organic ions may be there, some dirt may be there. So these things you need to remove through cleaning. There are different kinds of cleaning approaches are there. Okay, for example, piranha cleaning is one approach. So then you oxidize, or you grow oxide or silicon nitride layer on top of silicon. Okay, so this will act as a masking layer. Now what you do, you put a photoresist. So how do you put a photoresist? You drop photoresist. Photoresist basically a photosensitive polymer. Okay, so you drop a photoresist and then you spin coat. You spin the wafer or the substrate. So when you spin it, it will form a thin layer of photoresist. And as I said, there are you should optimize your layer thickness of the photoresist by rotation speed and time, okay, of your spinner. And once you get a thin layer of photoresist, you pre-bake it, say around 90 degrees centigrade or so in an oven, bring out, then you put it on the exposer. Exposer, what it will do, you put a mask. So what this mask will contain? Mask will contain basically your design. Okay, say maybe your source and drain, maybe your gate, whatever your design is, one layer of design will be there in the mask. The mask is made of chrome glass, so according to the design there will be opaque space and the transparent space. So what you do, you expose your photoresist through this masking layer with a UV light, and this UV light interact with the photoresist and property of the photoresist where it is interacting. So for example, in this portion, okay, only because it is interacting in this portion, the opaque, through the opaque portion, the UV light will not be able to come. Okay, so this portion, this resist will be, the property of the resist will change. Okay, then you do a post baking. So you heat up the substrate again in an oven, bring bring it out from the oven, you put it in a developer. Developer is basically a chemical solution which basically removes resist from the portion where its property was changed. Okay, so here the resist is removed. Then you etch the oxide. So you etch the oxide from this part of the substrate, because other part it is protected by the resist. So you remove the oxide, you end up with this structure, and then you remove the photoresist. So that is called stripping. This technique is called stripping. So you strip out, stripping. Okay, you strip out the photoresist and you end up with a structure like this. So you see, whatever your mask is, this is your mask. You are basically replicating whatever present in the mask on your silicon. So this is basically nothing but the intention of lithography. So then you can do various things. You can create source here, okay, or you can make a gate here. Depending on what is your objective, you can do that. Okay. Now the thing is, there are two kinds of photoresist. One is positive photoresist and one is negative photoresist. Okay. Now say if I have, this is my silicon wafer. On top of silicon wafer, this is my silicon dioxide. Okay. I have photoresist and I have masking layer. Okay. Say this is my mask. So UV light will pass through this. Now if it is negative photoresist and if it is positive photoresist, then the design will ultimately will be different. Okay. So in case of negative photoresist, once you, so this is my silicon wafer, this is my SiO2, and you will have resist here. Okay, after developing. So you see, in case of negative resist, after developing, this part will remain where it is interacting with the UV light. So in case of negative resist, where it is interacting with negative uh, uh, resist, the UV light, that part will remain after the development. What about positive resist? In case of positive resist, this is my oxide layer. After development, okay, those part will removed where it is interacting with the UV light. Okay, right? So in case of negative resist, after interaction with UV, this the exposed portion becomes more robust and they remain. And the opposite things happen in case of positive resist. Okay, then what you do, you basically use you etch, okay, etching. So you etch the silicon dioxide, right, and then you stripping your resist. So you see the pattern is like this. So you will end up with oxide here. What about here? You etch the oxide layer, so this is oxide and this is photoresist, and then you strip or remove the resist. Okay, so you end up with this pattern. So uh, depending on uh, your usage of resist, your pattern will be opposite. You see, so this is with positive resist and this is with negative resist. So you have to keep in mind what kind of resist you are going to use for your photolithography technique. Now this photolithography, this arrangement can be of various type. Okay, one is known as I mean, this optical exposure method can be of two types. One is shadow printing, sorry, shadow printing, and other one is projection printing. So this shadow printing again can be of two types. One is contact printing, and the other one is proximity printing. What is contact printing? Here mask and the substrate are in contact. So if I have a so this is my substrate, silicon wafer. I have my oxide, I have my photoresist, and then I have the mask, right? And then I have like a lens, UV source, okay, from which UV light I will get and all that. So here, as the name suggests, contact printing, so the mask and the substrate are in contact. You see, mask is on top of resist. Okay, so mask and substrate are in contact. What about proximity printing? In proximity printing, there is silicon substrate, say my oxide layer and my photoresist. Okay, but there is a gap between the substrate and the mask in proximity printing. Okay, and then there is UV light, right? So, but there is a gap. So, there certain gap is there. So, this is proximity printing. So, in case of projection printing, we get very high resolution because, sorry, in case of contact printing, we get high resolution because the mask and the substrate are in contact. Of the order of 1 micrometer we can get. Okay, so our initial lithography system is like this. Then people move to proximity printing. Here maybe 2 to 3, 2 micron or more than 2 micron resolution you can get. What is resolution? Resolution is minimum feature size which you can achieve. Okay, that is resolution. So now they have their own advantages and disadvantages. So in contact printing, as this mask is on top of the substrate, they are physically touched each other. It might happen that marks will be contaminated. So some dart might be from photoresist surface might come in contact here. Okay, might come in contact on the mask. So if you use that contaminated mask where you have somehow the mask got contaminated by the photoresist or by the substrate, okay, if you use that mask for subsequent, because you will use the same mask again and again, right? So that will basically damage, I mean damage means that will basically your device will not be proper, right? Because then on wherever your dart is connected, okay, that part will be opaque for the UV light, right? So this technique, in contact printing technique, there is a chance of uh, low lifetime of the mask. Okay, whereas in case of proximity printing, you see there is a gap, so you will be able to improve the lifetime of the mask. Okay, because it is not touching to the substrate. But here the resolution is poorer compared to the contact printing. Why it is poorer? Because this UV light, when they are passing through this mask, due to diffraction, I think you know what is diffraction. From these edges, it might go diffracted and might go to the portion where it should be opaque. Okay, it might reach the opaque portion of the resist, and if it goes to the opaque portion of the resist, when you develop it, this part of the resist will also be developed and will be removed. So your device will not be proper. In other words, resolution will hamper. Okay, so in proximity printing, resolution might be an issue, but your masking, your mask layer lifetime will improve, right? Usually the critical dimension for achieved for proximity printing is it is possible to show it is around root over lambda g. Lambda is the wavelength of the UV light and g is nothing but the gap between the mask and the substrate. Okay, so as you increase g, your critical dimension will deteriorate. Okay, now so there is another kind of lithography technique. As I said, this is projection printing. So in case of projection printing, uh, in fact nowadays most of the in industry all are projection printing people use, but in labs you can use proximity printer. Okay, proximity printing lithography setup. But what you do in projection printing? In projection printing, you can get much higher resolution, because here you use very complicated optical system where a only, so this is my wafer, so only a small portion of the mask will be used to write the wafer, and then you move this mask and keep on writing. Okay, and there is sophisticated lens arrangement so that you can get higher resolution. Let me repeat it once more. The projection printing, the setup is more complicated. Okay, that is the drawback, because here you are repeating the exposure one by one through the entire wafer. Okay, so you expose certain portion and then you move the mask, you expose the side another portion, and you keep on repeating that. So this entire process is a bit complicated, but you can get much higher resolution through projection printing. Okay, I am stopping it here, the lithography, the photolithography part. But you see, in photolithography, it is difficult to get sub-micron level of resolution. Okay, in conventional photolithography technique, of course, you can improve the situation by using immersion lithography and all that, but let's not go in that direction. But what I want to discuss now is e-beam lithography. So in e-beam lithography, okay, e-beam lithography, here we have, instead of UV light, here we will have electron beam. Okay, again there will be substrate, there will be silicon wafer, there will be silicon wafer or other wafers, there will be silicon dioxide layer, and on top of silicon dioxide layer there will be a resist, and this resist is, for example, PMMA is a kind of polymer used as a e-beam lithography resist. So this resist interact with electron beam and its property will change, and all you have to do is basically then use it in the developer to remove the resist and do the similar process what we have discussed so far. these process steps, okay, you have to perform. So the only difference here is in e-beam lithography, instead of UV light, you use electron beam. Okay, and another advantage of e-beam is you don't need any mask. You don't need any chrome glass kind of mask. What you do, you make a design in a CAD software, okay, computer aided design software, say AutoCAD or something, using some AutoCAD kind of software. You design your mask and you ask your electron beam to write on the photoresist, or electron beam will incident certain part of the photoresist according to your design. So you don't need mask, you just need electron beam, and of course you have to manipulate the electron beam, okay, so that electron beam will be incident on a specific place of the photoresist, right? So how this e-beam machine looks like, I mean, I just let me draw it very, I mean, a crude schematic of e-beam machine, okay. So e-beam machine contains a electron gun. This is an electron gun. So electron gun may be of two types. It can be thermionic or field emitted. What is thermionic? Thermionic is you heat up the gun, electron will come out. That is thermionic. What is field emitted? You applied high electric field and electron will come out from the tip. Okay. So this electron gun, there will be of course an anode. So this electron gun is cathode, okay, and there is anode. Anode, you in the anode you apply high voltage so that this electron will be accelerated, and there might be an aperture through these in the anode plate so that electron can go through, okay. Now these electrons, there will be series of lenses, okay. So these lenses, what it will do, they will focus this electron beam. So they will, so electron beam when it will travel, it will diverge, and this electromagnetic lens, so you can't use optical lens, right, because it is not light. So you need to use electromagnetic lens, okay, to push those electron to its focus, okay. So you use series of electromagnetic lenses. You also need to use, so this is say my electromagnetic lens 1, it can be there be 2, 3 and more, okay. It is also known as condenser lens, okay, condenser lens. So this is known as blanking plate. So if you apply voltage in the blanking plate, so it will blank or it will prevent the electron to pass through it, okay. And then again there will be condenser lenses, okay. So there will be say second condenser lenses and so on, right. And ultimately there will be limiting aperture, okay. So which will basically remove, which will allow electrons which is very close to the center of the line and doesn't allow electrons which is away from the axis, okay, and so on. So there is a lot of different arrangements, and ultimately this electron beam will incident on your substrate. So there is this oxide layer, then there is this photoresist or e-beam resist. Okay, so on this resist it will incident and it will interact or write on the resist. Okay, so there will be some other arrangement is there. There is electron detector. So from there you know how much electron is incident on the substrate and so on and so forth. So there it is not this this machine is of course much more complicated compared to UV system. Okay, but this, why this is very useful? This is very useful because with this machine you don't need mask. You see, you don't need mask, you can directly write on the photoresist. Another is resolution is very high. Why the resolution is very high? Resolution is very high because you see wavelength, as you remember, wavelength associated with electron is much lower compared to you remember we found out the de Broglie wavelength of electron. Okay, so wavelength associated with electron is much lower compared to the UV light what we use. Okay, so you see we will be able to write much lower feature size or much smaller feature size if you use electron beam, right? What is the drawback? So these two are the advantages. You don't need mask because you are directly writing on the photoresist, and your resolution is much higher. Maybe you will be able to write few nanometers. Okay, whereas here you write maybe micrometer or several hundreds nanometer, not more than that, not less than that. Okay, but here you can do it few nanometers resolution you will be able to achieve. What is the downside? Downside is you can't it is a very slow technique because it will write a particular place, then the electron beam move, you write another place, then the electron beam move, you write another place. It is not like UV photolithography technique where you on a single exposure within few seconds you will be able to write the entire substrate on entire substrate, because there is a masking layer. All you are doing, you are switching on your UV light, and that UV light will go through the masking layer through the transparent portion and interact with the photoresist. So few seconds, few tens of seconds are required in case of optical lithography, that exposure time. But here it might take hours because it is writing on the resist itself, the electron beam, and electron beam is very tiny, because if the electron beam is very wide you will not be able to get high resolution structure, right? So the downside, it is very slow, even it takes several hours to write your features on the substrate, right? So there are different so this is scanning method. So it is basically scan. This electron beam will scan the photoresist. Okay. So there are two kinds of scanning method. One is known as raster scan, and one is known as vector scan. In raster scan, you basically scan the entire wafer. The electron beam will scan the entire wafer, and according to the design, wherever you need to write, it will write there. Okay, but you need to it will scan the entire wafer. Okay, and wherever according to the design, it will write that part on the resist. In case of vector scan, it will scan only the part where it will write. Okay, only the part where it will write. So raster scan is much slower process compared to vector scan, but vector scan you see it is little bit complicated compared to raster scan. Now apart from it is slow, there are other constraints associated with electron beam lithography. What are those? Although you remember we find out the wavelength associated with electron, probably you notice that the wavelength is very tiny, maybe few hundred picometer. Of course, that depends on energy, how much energy you are applying. You remember we use kinetic energy of to calculate the wavelength, right, of the particle associated to which we are finding the wave nature. Now, this still in case of electron, the maybe the wavelength is few hundred picometer maybe, okay, but when you write, actual feature size is few nanometer, minimum feature size. Why it is so? Because there are some other constraints. What are those? For example, one is known as, so you see there are silicon, there are photoresist here, okay, and this electron beam is going inside and it is interacting with the resist. So once it comes inside the resist, what it will do, it will scatter, these electrons will scatter, okay. So you end up with in a much larger place, whereas when before reaching the photoresist it is much narrower, but once it enters the resist, it will scatter, okay. And so due to this scattering, okay, the resolution will degrade. Apart from that, these electron will interact the electron in the resist and can generate secondary electron. So these secondary electron can move and interact with the existing photoresist, okay. So this is known as proximity effect. What is proximity effect? Proximity effect is electron beam might produce secondary electrons in the resist, which can expose resist which are not directly under the electron beam, okay. So I might be this portion is directly under the electron beam, but actually other part adjacent to this directly exposed portion will also be affected. This is known as proximity effect, okay. The electron might scatter and come out from the surface. So this is known as backscattering. Electrons scatter from the surface, cause unwanted reaction and takes place outside the focused electron beam. So this electron might come out like this, and that way again some part which is not actually should expose, but it's going to be affected because of this backscattered electron, because of this proximity effect. And so, and I mentioned this is very slow, so throughput is poor. Throughput uh, from this machine is very poor. You see, time is money. If you can't produce it very quickly, okay, it will make things very expensive. And also stability might be an issue. Stability of what? Stability of electron gun. Because if the gun runs for hours, okay, so how you are doing? You are heating up the gun, or you are applying electric field which is basically bring out those electrons. But if you do it for hours, several hours, that might create an issue of the reliability of the electron gun, okay. So these are some of the drawbacks, but let me tell you that in commercial foundry people don't use e-beam lithography, because then the process cost will be huge, okay, because simply because throughput is poor. So people don't use the beam lithography, but in research lab, okay, people use the beam lithography in research lab to develop a very tiny structure of few nanometer, okay. Maybe you want to make a single electron transistor, you need e-beam lithography, you can't do it using optical lithography, and so on. So these two I thought that I should discuss. So I briefly discuss e-beam lithography and optical lithography. Hope you understand this. I will see if I have some note, because I don't have I don't usually cover this part in earlier classes. In earlier sessions I haven't covered this part. So I need to see if I have a note. I will then circulate it to you. But I thought that I should discuss this, because then it will help you to understand the fabrication process steps. Okay. Do you have any questions? Do you have any doubt?
No, sir.
Okay. So have you come across with e-beam lithography before?
Yes, sir.
But it was discussed in VLSI technology course.
It was discussed in VLSI technology course. Okay, excellent. And also photolithography, it was discussed, I think.
Yes, sir.
Okay, 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 excellent. So we'll stop here today. In the next class, I will see what I can cover. Okay.
Sir,
Yeah, please go ahead.
uh, sir, can you explain why do we use the
Sorry, your voice is cracking. Once more, please tell me, why do we?
post bake after doing the
Okay, so there are two baking. One is pre-baking, okay, another is post-baking. So it was found that if we don't use post-bake, then the development is not that good. You remember we need to. So if you look at the process steps, you need to develop. That is basically you need to remove the photoresist. So this drawing is for positive photoresist, in fact. So you see this for positive photoresist, okay. What happens when it come in contact with UV light, okay, its long chain, basically the long chain of polymer will cut, okay, from this portion. So that chemical change will take place. And what we do, if we don't use post baking, people found that this removal of this resist from this part will not be that good. So post baking is as important as pre baking. Pre baking will ensure the photoresist will stick to the substrate, and post bake will help in developing the photoresist. Okay.
Okay, sir.
Okay. So thank you very much. We will meet again in the next week. Okay.